Yeah, today we have Thomas Lam to talk about the twisted cohomology of matrices.
Yep, thank you. I'd like to thank the organizers for giving me the opportunity to speak. And I'm really excited to talk about this because I have so many experts in the audience. I'm seeking advice on a number of questions. So I want to talk about twisted cohomology, and so I have 2 hours. In the first half, I'll try to state the problem. The second half, I'll state the answer. The setting is for the first half, I'll take a hyperplane arrangement. And it will be defined over the reals. I'll just assume that for now. And you will denote the hyperplane arrangement complement. I'll always assume it's essential. And I'll have a matroid M that corresponds to it. So if this is a rank D arrangement, this will have rank 1 bigger, and the grand set of the matroid I'll denote by E, and it contains 0, which is the hyperplane at infinity. So this is E 0. So the projective arrangement includes 0. Okay, so this is just the basic setting that I'll be working with. Actually, for most of this hour, this is not important, but later on it will be. So just a complex hyperplane arrangement. And in the 70s, following sort of some work of Arnold, Briscoe proved that this the cohomology ring is generated by these differentials, dFE, FE, where this HE is the vanishing set of FE. So we pick some linear forms that cut out the hyperplanes, we write down these particular 1 forms, and the cohomology is generated by these. And let me write deRham cohomology because I kind of want to make the distinction between different kinds. Soon-ish after, yeah.
Without the 0, I'm not.
Yeah, so let's just write E. Yeah. Or you could take, if you want to think projectively, you would write generated by so you could do either way. If you wanted to think projectively, then it would be generated by d log of the ratios. So these guys all live in H1. And in fact, and not just is generated by, but actually as a ring, that this is isomorphic to just a ring of forms. So there are no additional relations. You just take the ring of 1 forms and you calculate what the ring is, and that's isomorphic to the cohomology. And that thing is called the Euler-Solomon algebra. So, and I'm going to write Euler-Solomon algebra, and it only depends on the matrix. So I write M here, and this bar here is because there's kind of 2 versions of this. One is for projective arrangement, and one is for a central arrangement, and this is the one for the reduced Euler-Solomon algebra. And it sits inside the actual Euler-Solomon algebra, which is isomorphic to an exterior algebra on this ground set E over the complexes modulo some ideal. So for the first half of the talk, it won't be important to me what the relations are, but it's got a presentation of the form, take an exterior algebra and mod an ideal. So if you take an exterior algebra on all of these, so including 0, then you get the whole Euler-Solomon algebra. And if you only take the ratios, then you get this reduced one. So, okay. Any questions Okay, so this is early, I think that's early 80s. The relations for this ring were figured out. By Olaf Solomon. I want to talk about the version of the story that was studied in the 80s and 90s a lot, which is a twisted version of this. So I have to introduce this twisting. So and I feel like maybe I'm going to try to write it a little bit more democratically this way, actually. So maybe I should have maybe I should have chosen slightly different notation there. So I'm going to write down this function that we're going to take all the linear forms, raise it to some powers, and the powers are some complex numbers. And for this to be a well-defined rational function on projective space, we need this condition. And it's a multi-valued, it's not rational. To be well-defined, it's a multi-valued function. So it's multi-valued when so if these guys are integers, if they're integers satisfying this condition, then it's a well-defined rational function of projective space. For complex exponents, it'll be a multi-valued function. This thing has a lot of different names.
The product is E, not A, right? Under the product.
Thank you. So sometimes called potential, twist, master function. So depending on what context, it's given a lot of names. So this thing is a multi-valued function, but a D of it is a one form, and it is a well-defined algebraic object. And by the form of it, it lies inside this this ring. So it defines an element in A1.
Why do we have to assume that the sum is 0?
Oh, because I'm including in this indexing set, I'm including 0. So these are linear forms on projective space. So by itself, it's not a function. Only ratios of them are functions. Yeah. So I need to impose this condition.
It's the log file, right? Or
Yeah.
the file file.
Is there a log somewhere?
Sorry. Okay, so associated to this one form, I'll write down a connection, and I'll indicate the parameters that the connection depends on. It's the usual exterior derivative, and then you modify it slightly by wedging with this one form. So we view this as a connection on rank 1 trivial vector bundle. So just on the trivial bundle. There's a version of this story for higher rank, but I'm just going to do rank 1 today. And then, so I'll say more about this, but I'll give you all the notation first. And then there's also rank 1 local system, which is the sheaf of local solutions to this. So the local solutions to this guy are basically the branches of the inverse of this function. And so this is, what kind of thing is this? This is a rank 1 system. So what is the data of a rank 1 local system? Rank 1 local system is up to isomorphism, the same thing as representation of pi1. So pick a base point in this hyperplane arrangement complement, and you get a representation of the fundamental group. Because I'm doing rank 1 local systems, it just goes into GL1, which is a little bit slightly boring. So to every generator of pi1, you associate a number. And what are these numbers? So over here, I'll draw a little picture. So here's my hyperplane arrangement. Here's my, let's say this is my base point. The generators of this pi1 is you go all the way to hyperplane, and then in the correct complex dimension, you go once around it in the actually usually I want to go anti-clockwise. And then you go back. I can draw going back. Okay. So that's those are the generators of pi1, and to each such generator. So this is H sub E. To each such generator, there's some loop gamma E. So this is my gamma E, and what will it be for this particular local system? It will be the number this, which I'll write as BE squared, where BE is defined to be so if A is an integer, then there's no monodromy. And let me just explain this. This is not so familiar. So let's suppose we were D is 1 and there's one puncture. The kind of function you might be looking at is the following function in the complex plane. Is like you might be looking at this function z to the a. So that could be, so a would be the same a minus a, and you would write this as xa log z. And you would have to pick a branch of log z. So, okay, if a is an integer, then you're fine, and there's no monodromy. If a is not an integer, you would write this. And different branches of log z differ by 2 pi I. And so if you go once around, anti-clockwise around the origin, z to the a will pick up this factor. So there's a minus sign because there was a minus sign somewhere else. Yeah. Okay, so right, so the reason to study this, at least as I understand the history, which actually I've only been learning the history recently, is from hypergeometric functions, that there's a generalization of the Gauss hypergeometric functions to hyperplane arrangements. This was studied by Matsumoto and Gelfand in the 80s. And they're of the type, so the reason to study this setting is you want to look at integrals of the form integral phi theta. Phi is the same phi over there. And you want to interpret this as a pairing between a homology group and a cohomology group. So in usual homology, you take a cycle and you can pair it with a cocycle. The cocycle could be a differential form. Then if you have to take a differential form, it's closed, and then you have a cycle, you can integrate, and that will be the pairing between cohomology and homology. Here we're going to keep track. The way we're going to keep track of this is that now things are a little bit different because of this twist, because this thing is multi-valued rather than single-valued function. So you need to work, the conventions are that that this twist is kept track of in the homology side. This is. So theta is some differential form, one of the things inside here. So theta is going to live inside here. And then we're going to pick some cycle. I will tell you what kind of cycles we're going to be looking at soon. But the cycle is going to be attached with some additional data. So that's an interpretation. The way to check that this so the explanation for example, for this formula up there, explanation for that is there's a version of Stokes' theorem for these twisted integrals, and to check that the Stokes' theorem works, you need some kind of formula that looks like this. So if you D this combination, then you can actually just act with this connection on the cohomology class. So the basic examples of these functions since the very beginning. Let me see. This function called this one's called the beta function. Studied by Euler, maybe in the 18th century. And this is this function is associated to what hyperplane arrangement is associated to is you take the affine arrangement with sort of two points removed. So in this case, capital E will contain three elements. This is the uniform rank 2 matroid. So this is U2, 3. And you put one of the points at 0, Z is equal to 0, the other point at 1. And there's also a point at infinity. This expression here is the phi. This is an example of an element inside the Onyx-Lotman algebra. Another example of a function that's related to this theory is Gauss's hypergeometric function, which you can get in this way. I have to remember all of this one. Somehow when I wrote down this formula, it has Z and X were swapped, so sorry. So the form is the same form, but now there's in this time there's one more point on the line, and the coordinates of the point are vary. The last point is 1 over Z, which could be somewhere over here. So you add this extra point. Yeah.
Are you saying the integration measure is dz over z times 1 minus z? And then in what way would we achieve that as a d-log form? Since it has.
This thing is actually d1 minus z is actually equal to d of z over 1 minus z, or plus or minus. You can calculate this, but it's d-log of, it's actually just d-log of 1. So other main examples, the Selbert integral and which corresponds to the complete graphic matroid, and the Apple and Lauricella functions, which are all one-dimensional examples. They're all one-dimensional affine arrangements.
Why was Gauss looking into this kind of things?
Actually, I don't know why Gauss was looking into these integrals. There's I think it has to do with finding differential equations which have nice solutions going beyond. So you have these linear differential equations with some coefficients. The coefficients will depend on x, and you're looking for classes of differential equations which have solutions that you can understand well. And there is an attempt to classify these nice ones. But I don't know the original reason Gauss wrote this down.
What is gamma in this example, in this situation?
Oh, sorry, gamma here, gamma is the interval 0 to 1 in this example, in both examples. 0 to 1. And then the twist is this thing, and then and then the form is an element of the Euler-Solomon algebra. So you can look at these, and I want to say that actually I think there's still a lot about these integrals, integral functions that's still unknown to this day. For example, there's still lots of questions about monodromy groups, especially when you increase this to a higher rank. Okay. So okay, so I'm going to go further. I'm going to make an assumption here, which will be pretty much in effect. So I'm going to impose a non-integrality condition. If you don't know what indecomposable means, it's okay to just assume it for all flats. If you don't know what flats are, you can just assume, you can just take the condition that no combination of any of them sum to an integer. But this, and in fact, some of the theorems were originally proved with these weakenings that I just said.
Indecomposable means what? Matroid people connected?
Yeah, it's a connected. Yeah, the restriction to that flat is connected. And I think in the late 80s, so under this assumption, Kono proved that, or maybe one of the weakenings that I just said of this assumption, proved that in this so if you take this local system and you take you can take its homology with coefficients in this local system. So we'll have some examples later on. So it has cohomology and homology groups with coefficients in this thing. And there's more than one version that you can do. There's one that's sometimes called around more, but somehow in this context, people usually say locally finite. And what he proved is that the usual homology is the same thing as locally finite homology. And the dual statement is that the compactly supported cohomology is isomorphic to the cohomology. It's definitely not true if you don't impose something like that.
Thank you. Maybe
Sorry. Yeah. Thank you. So if you have a compactly supported differential form, certainly you can think of it as a closed compactly supported differential form. You can definitely think of it as a differential form. So there's a natural map this way. Same thing if you've got a finite chain, which is closed, then you can definitely think of it as a locally finite chain. And the slightly surprising thing is that these are isomorphisms. The inverse maps are called regularization. So rank goes backwards. So you can take a form which is not compactly supported, for example, something in the Euler-Solomon algebra, and then you can go back and represent it by a compactly supported one. Necessarily, it won't be algebraic, so it will involve some analytic aspect. And also, the sort of as a corollary of this, these groups vanish for a not equal to the middle or top dimension, depending whether you're doing real or complex dimensions. And also something that separately we know is that the dimension of the one that doesn't vanish. So all of these will have the same dimension. All four of these guys have the same dimension. For HD, so let's just write this one. Oh, okay, that one. The dimension of this is just the beta invariant, which is the Euler characteristic of U.
So for the vanishing, like star is necessary, but for the two isomorphisms, is star also necessary?
Yes. Okay. So what's the proof? What's the proof of this? So take this sheaf, locally constant. Take this locally constant sheaf, and take a compactification of U, and look at the shriek and star push forwards. So the shriek star push forward will calculate this guy. The star push forward will calculate this guy. What you have to do is to prove that these two are isomorphic. The lower shriek push forward and the lower star push forward are isomorphic, which is the same thing as saying that stalk of the star push forward is 0 at infinity. And to prove that the star push forward is 0 at infinity, you have to show that the solutions cannot be extended. And that's exactly the condition that there is monodromy. So where's my monodromy here? So if you take this guy and you ask, can this local section be extended to the point z is equal to 0? The condition that it can be extended is that a is not an integer. And so that's where this comes from. So then you pick the compactification to be the one where the minimal wonderful compactification.
I think you miss the -1 to the dimension of U on the minus. Because
Thank you. Yeah, sorry. Okay, so there's another thing that you can do. So how do you calculate one of these groups? Well, there is so at least this guy, according to this theorem all the way back, like Briscoe's theorem all the way back here, it has a purely combinatorial, there's a purely combinatorial way to think about this ring. You just take this ring, it's got some generators labeled by E, and then there's some relations, there's a list of relations. So you can form a complex by taking this ring and taking omega as your differential. Omega squared is 0, so this is a complex. Also, d is 0, so this is actually the same thing as the connection. So, like this map is the same thing as applying the connection because D is acting by 0 on these forms. They're all closed forms. And so the theorem is again with the same assumption, it turns out. Due to Arnaud, Schechtman, Schechtman, Terrell, and Varchenko, slightly different assumptions. I mean, the main idea is and these guys changed this, like made the star better. And so they proved basically Briscoe's theorem for twisted cohomology, which is they said that this complex correctly calculates twisted cohomology under the star assumption. So the natural inclusion of this complex into the global sections of the sheaf of algebraic differential forms. So this is some complex, and inclusion is a quasi-isomorphism, and that implies that we have that the cohomology of this complex calculates the cohomology of the connection. And I'll define the cohomology of this complex, which is now it's kind of a purely combinatorial thing, modulo the fact that there are these complex parameters appearing in this differential. I might stop writing the because they all vanish except for one group, so I don't have to write the exponent in case, yeah. Okay. So I think I can make I can now write down the main definition.
So if you say that cohomology with the connection area, that's the same as the cohomology with the coefficient in the local system.
Yes, yeah, I should have said that. Let me write it down here. There's in the usual world, there's deRham's theorem. And let's B here for Betti. So there's a purely topological thing that you can do, singular cohomology, tensor that group with C, and then you get deRham's theorem that says that this deRham cohomology is isomorphic to the Betti. There's a twisted version of it. I do need the notation for it. So there's a map, like I said, the pump for comparison, which goes from this and it's an isomorphism too. This doesn't with the correct definition of top one, this doesn't require these assumptions. So if you define this top one using smooth forms, then with no, then this is nearly by definition. Okay. Yeah. So there's a version of twisted version of deRham's theorem. Okay, so the main definition, which is the intersection pairing, appears to be first considered by Cho and Matsumoto in the 90s, early 90s, but and so I will so I'll be using these theorems, but I'm going to the corresponding things also work over here since the isomorphic. So I'm going to look at the pairing between this twisted cohomology group and this twisted cohomology group. Takes an element here, an element here, and pops out a number. And the definition of it is you take this guy and apply the map in Kono's theorem to one of the factors. For concreteness, I'll apply it to the first vector. And so now I get a compactly supported cohomology class and a usual cohomology class. And there's a Poincare duality between these two groups. So this is Poincare Zodiac duality. To be really concrete, what you do is if you give me a form here, and you give me another form here, then you map it to and for reasons, I prefer the version where you do this. So this is so normally if you have a differential form on this open thing, you can't always integrate over the whole space. But because tau, one of the two is compactly supported, this thing is compactly supported. So this integral does converge. And that yields this yields the Poincare duality. I want to think of this as a bilinear form on a single vector space. So the way the duality works here is that you have to put, we're talking about sheaves, you have to put a sheaf here and the dual sheaf here. But I want to think about it as a bilinear form on a single vector space. So I'm going to use the isomorphism in this theorem over there. And so there's isomorphism this way. But actually for this collection of parameters, the cohomology is actually the same. If you change A to negative A, you change omega to negative omega, and in this complex, the last term is you just take one of the mod omega of everything else. If you change omega to negative omega, the cohomology is the same space, the same quotient space. You're just quotienting by negative of the image. So then I'll take the same guy and then I'll tensor those things and I'll land in here. And this is the thing that I'm going to denote the deRham intersection pairing. This is the definition of the deRham intersection pairing on the Aulick-Solomon algebra of, sorry, the cohomology of the Aulick-Solomon algebra of a hyperplane arrangement complement.
So local system and the dual local system. That's one thing as well.
Yeah. So the local system, yeah. So these guys are, yeah, I should have written this earlier. This connection and this connection with minus the parameters that dual. And then this thing and this that dual. So the Poincare duality will pair a compactly supported cohomology group for some local system with the usual cohomology for the dual local system. And then there's another version.
The local system having the same cohomology as the dual local system is something special.
It's weird. I agree. It's weird. It is definitely weird. But it makes the answer nicer to really think of it as a pairing, to think of Poincare duality as a pairing on just one vector space instead of two. Somehow, if by doing this you get good combinatorics, and so there's also a very similar definition, actually occurred very slightly earlier than that paper, I think, due to Shita and Yoshida. I mean, definitely they influenced each other, which is that they did the thing in homology, but in the so this one is about differential forms, because the way they intended one to calculate it is that you did this operation on your differential forms. There's another version, and I'll be quick here because it's nearly the same, but was defined by these guys in homology. Is you take some locally finite or Borel-Moore classes, and you try to pair them. And the way you pair them is you convert one of them using Kono's theorem. You convert one of them into a usual homology class, And then you have, again, this is the Poincare duality in homology, and it has an explicit formula. The explicit formula is, suppose I'm trying to pair. So this thing I denote. I'll put a B here for Betti. I'm going to try to pair a class that looks like this with a class that looks like this. And the where this is some choice of branch. So you have to make, you're basically choosing, every time I write something like this, you have to make a choice for which log you took. So how do you pair two classes like this? You move one of them slightly to a homologous class until the intersections are transverse. And then you sum over all intersection points. The intersection points will be just finite. I mean, there'll be points because we're working in a d-dimensional complex space, and I took two cycles of dimension d. And then you take the topological intersection number, and then you include information about these branches. So you include the information about the local system. Something like this. And why do we need it to change one to a normal homology class? Is you need the sum to be finite. So with this now being a homology class, this is a formal infinite sum. This is a finite sum. This summation will be over finitely many times. And so they define this to be the what I call the Betti homology pairing. I think so. Before I stop, I think I want to tell you what the answer is in maybe this case, and also very quickly state the theorem, which I talked about in the second half. So the main theorem is closed matroidal formula for these two things. I have to explain sort of what exactly that means. Second part is that these formulas are tropical, so they can be expressed purely in terms of the Bergman fans of the matroids. And three, it turns out that there are sort of four pairings, and some of them have been are close to things that have been studied before. This guy and sort of the dual symmetric bilinear form induced on the homology. They're very close to things studied by Schechtman and Varchenko. This one is very close to something studied by Varchenko. There's another one, and then I have some new formula that seems to be new. There's this one, which is Keith and Yoshida's definition. This appears to have never been studied before. This thing, the bilinear form induced on cohomology by this pairing is something that Varchenko looked at, called the Matroid bilinear form. So what special cases were previously studied? Actually, previously, these formulae were available in these cases, in one-dimensional cases and in the cases of generic arrangements. And also for one other example, which is the case of the complete graphic matroid.
The true Matsumoto one is the pairing upper deRham
Yes, upper deRham.
and lower deRham is not introduced yet.
The definition of this is the pairing on homology. So it turns out that this pairing is, well, in the case of hyperplane arrangement, this is a perfect pairing. So this is a non-degenerate bilinear form. it induces a dual bilinear form on the dual space, which is homology, and I call that dual bilinear form this. It turns out it also has a combinatorial formula. In fact, the combinatorial formula for this is new, so maybe I shouldn't. I mean, they definitely looked at this this form, but at least yeah, they didn't have a combinatorial, at least not the one I like, combinatorial formula for this homology pairing. So there are 4 pairings, and one of the mysteries is there's a geometric definition. These 2 definitions are geometric definitions of these 2 pairings. The inverse pairings have really nice combinatorics, but as far as I know, there's no separate geometric definition of them. They're just defined as the thing induced on the dual space, but it turns out the dual ones actually have nicer combinatorics than the original ones, which was a kind of a puzzle to me. Let me just quickly give this one example, and then I'll stop for the first half, which is we'll take the Betti, the Betti arrangement. So there'll be, okay, let's have 0 and 1, and let's associate the parameter A1 to this point, the parameter A2 to this point. In this case, the beta invariant of this matroid is 1. So this is a one-dimensional vector space, and one possible basis of this vector space is the form that I just erased, this form. So you can take omega is dz over z 1 minus z, and you can ask to take that form, which is a possible basis element for this cohomology, and ask to pair it with itself under this pairing. And it turns out that the answer is simple. It's this formula. And because we're working under those assumptions, when you plug in A1 and A2 are not allowed to be 0. 0 is an integer. You can also take the pairing over there. Yes, you can also take I to be the interval from 0, 1, and you can ask to pair this guy with some declaration, which I have to say a little bit more exactly what branches I pick. I can take the pairing with this Betti homology pairing, and it turns out that the formula. Okay, but this is not completely precise yet because I have to tell you, I have to still pick sort of a choice of log for those things. I want to just quickly end with why Choma and Matsumoto actually did this calculation. They did this calculation especially for this particular case because they were interested in the following identity, which you can deduce from these 2 calculations, which is write it down. This is called the quadratic identity for the beta function. And the way you get this from all of this formalism is you write down your pairing. And you also write down the isomorphism here. Some isomorphism here. The coefficients of this isomorphism. So once you pick a basis of this cohomology and pick a basis of the homology, which gives you a dual basis of the cohomology. Once you pick bases for everything, the coefficients of this map, which is an isomorphism, that's a matrix where the matrix entries are called periods. They are integrals. So so this map is a period matrix, as is this one. And the two pairings, basically let me just write it up here. Is if you take the deRham cohomology pairing, then you apply this comparison map. You can now take the Betti pairing. In cohomology, which is the inverse to the pairing defined over there. These two things are equal, except that I have a, I prefer to extract the 2 pi I, so I'm good. So if you write down what this is, then you see that, so this is an identity of matrices. In this case, it's all of the matrices are 1 by 1. This is a one-dimensional vector space with some distinguished generator, one-dimensional vector space with some generator, one-dimensional. So the generators are these guys. Once you write down all of these things, this commutative diagram gives you just some identity of numbers. In the other hyperplane arrangements, give you some matrix identity. If you multiply all the beta function is the entry in this matrix, this beta function is the entry in this matrix, and then this number is what you get here. This number is inverse of what is actually inverse of this. This weird trig thing with the 2 over I is actually 1 over this expression. Okay, I'll stop here for the.
Yeah, so let's have a quick question answer and then have 5-minute break. Okay.
Yes.
I thought the period matrix was supposed to pair cycles and cycles.
Yeah, but you can write it as, so they will be coefficients in the expansion. So this, if you take a differential form here, take the image of here and try to expand in the due, basis due to cycles, then the coefficients of the expansion will be periods, will be the integrals. Yeah.
Can one do similar things for arrangement of hypersurfaces? You don't have a matrix anymore, but not much of this thinking still do somehow.
I can't do anything, but I mean, you can certainly define a lot of things. There is a question of, I mean, one of the things that's really special to this case is the theorem that I erased from here, which says that the algebraic deRham cohomology of the connection can be represented purely by log forms. So that is usually not true in general. You can't just write every cohomology class as a log form. So the fact that it's combinatorial in this case is kind of due to Briscoe's theorem, that it's sort of a combinatorial thing.
Also, I think of this interval I as a finite cycle.
Oh, no, they're not. They're locally finite cycles.
Yeah, but here I want to somehow make it informed.
Oh, you mean how do I apply reg to it?
Yeah.
Yeah, actually, I will do this in the second half. I will calculate this for you, that particular one. I'm glad you asked about this one and not this one, because I had to choose between the two, and I decided I'll tell you how to do this one.
They are all similar difficulty.
Well, this one you have to write locally. You have to write this cycle as a finite sum, and this one you have to change this form into a compactly supported form. Yeah, I think it's kind of they're different. They're different calculations. That's why I like emphasizing that one's Betti and one's deRham. They're very different calculations. And those two papers, when they first did this for this example, when they first did this for the one-dimensional case, it's like the kind of no common aspects in the calculation.
Yeah, so let's resume in 5 minutes. Yes, we'll continue the second part.
Yeah, so I just wanted to point at this this picture a little bit before I tell you the answer to the problem, because there's something. So what I'm going to tell you is that this pairing here is matroidal, and there's a formula for it. This pairing here is matroidal, and there's a formula for it. there's something that I'm trying to figure out now, which I sort of want to ask all the experts, is about how to understand these things in terms of Matroid realization spaces. So the way that I'm sort of, if you give me a hyperplane arrangement after this package of data, there's a matrix up here, and some matrices, and these matrices are really hard because they contain inside them these like beta functions, hypergeometric functions, and so on. So on the other hand, these things down here, I have a matroidal formula, and I want to ask to try to make sense of the question of what, given a matroid, what are all the periods that fit into this diagram? So I know this matrix, and I know all of them satisfy an identity. And I want to know what things can I put in here. And this is something like a period realization space of a matroid. And there's something slightly more general than that that you can ask about, is whether you can have a matroid that is, for example, not realizable. Can it still have a motive? Can a matroid, so you associate to a matroid all the motives of the mixed motives of the hyperplane arrangement complements with that matroid. So that's a way to map from the matroid realization space to category of mixed motives. I want to ask whether there's a possibility that you can have a matroid that doesn't have a realization in the usual sense, but has a realization inside the category of mixed motives. And I think that this is one way to get some data on this problem. So if you thought about periods and motives and matroid, then I'd like to ask you questions. Okay, so let me answer June's question. Is how do you calculate? I think I hit it here. How do you calculate that Betti homology intersection pairing that was on the board previously? So here I'm taking my two cycles are the yellow and the blue, and they're the same thing. They're both the interval. So the D is originally, it's just the interval from, so here's 0 and here's 1. I'm just taking this is my int I from before, and I'm trying to calculate how to intersect this guy with itself. And so first of all, the reason this is a locally finite cycle is you're supposed to think of it as an infinite sum of little segments that get closer and closer to so you take a little segment, which is a chain, a one chain, you take another one chain, and you keep putting more of them. And so there's an infinite formal sum of one chains. Okay, so the claim is that in H1, this locally finite chain is homologous to this actually finite chain with the twisting. And the way it works is you take one one chain, which is this circle here. It looks like a circle, but it's not. It's actually a one chain because of this twisting. So the value of your function phi here is different to the value over at the other endpoint. So it doesn't close up to be a closed. This is not a one cycle, this circle. And I'm writing this expression for this thing. So the monodromy is B0 squared. So that's the monodromy around 0 is B0 squared. Monodromy of 1 is B1 squared. And if you do a calculation, there are some coefficients you need to put. So for this thing and this thing to be homologous, you have to weight this part of the cycle by this number, which is the difference. It's the difference, sorry, it's the ratio of the value at this point and at the value at this point of the twist. And then you just do a normal thing here. You just add a segment, and then you also add this cycle like that. And what you can prove is that the difference between this and this is equal to the boundary of the two-dimensional the two cycle, which is locally finite, which is the interior of this disk and the interior of this disk. Yeah. And by interior of the disk, I should actually draw a picture. So to prove that so to say that the same homologous, I have to take the difference and show that it's the boundary of something, and the band is the boundary of this thing. You have to cut it here slightly because of the monodromy issue. And same thing over here, you do something similar over there. Now, having replaced this locally finite cycle by this actually finite cycle, I want to intersect it with this. And what I do is I make a small perturbation of the other thing. So the other thing was also an interval. So the other cycle that I was trying to intersect it with was this one. And I just want to perturb it very slightly so that the intersections are transversal. And so I just did this thing. So there's one intersection point, which is pretty close to here, one intersection point somewhere in the interior of this interval, and another intersection point here. And with the correct signs, so there's a contribution of one here, one here, one here, but then there are also these coefficients. So that leads to the final answer, which was, the final answer which I wrote down was 1 plus 1 over minus 1 plus minus 1 is the intersection number of these two cycles, twisted intersection number. Okay. Let me see if there are any questions about it. So this was so for one-dimensional cases, so Kita and Yoshida wrote down the answer for this for one-dimensional cases. I should say that when they first wrote this down, it was a pairing between two different spaces, and it wasn't a symmetric pairing. I'm still a little bit surprised, but there is a way to set things. There is a way to set things up so you get a nice symmetric bilinear pairing with really nice combinatorics. And I'm going to tell you what the answer becomes when we do that. Okay, so I'm going to try to tell you what the answer is in terms of this thing. The Bergman fan of the Matroid, sitting inside B. So first of all, I need a little bit of terminology. So the corresponding to this Matroid is M, and then there's the lattice of flats of this Matroid. Let me draw it over here. I guess I'm not currently including. So okay, there's some more. So there is the line at infinity, which or we could picture this as a projective arrangement and not include it. Okay, so there's also, I guess there's also a zero. There's also a zero here and some other stuff. Some stuff at infinity that I'm not drawing right now. So I'm just taking the lattice of flats of the hyperplane arrangement. And so what we do is, so this is sitting inside the bigger lattice of flats of the Matroid. So you take a flag, a complete flag.
Should this be?
The spacing was there should be no space.
Sorry. Yeah, so let's take a complete flag of flats. This is just a flat photo as the empty set. E. So take a flag, then define a cone. And I'm going to do something slightly, it's not one of the most common choices. I'm going to define the Bergman fan as an R minus one dimensional fan, but sitting inside RE. You just take these indicator 0, 1 indicator vectors for each flat, and then they will be the generators of your cones. Normally, so just like a slightly subtle point, normally you would include this vector as well if you worked in RE, or you would mod R of the all ones vector, and then you would omit that one. For some reason, I want to it's an extremely minor thing, but I like to do this one. So for example, and then the Bergman fan is the union of all these guys, and together with all their faces. So you would, for example, you would take a possible flag would be something like this. Yes, I should put 0 in here. What I would do to get the this cone is I would take but one generator for this, one generator of this, and take the span, and it's a positive span. So if I take this flag, then I'm getting this cone, which is span of this basis vector together with this. So it would be a 2-dimensional cone. So the union of these things is the Bergman fan. Now, I'm going to work in the so the formula I give. So one slightly weird thing is one of the formulae I give requires an oriented matroid, and the other one only requires a matroid. But I'm going to work with an oriented matroid, orientation of the matroid. So given if you give me a tope, so if you're not familiar with oriented matroids, I'm just talking about one of the chambers of the hyperplane arrangement. So you this thing here, that would be a tope. You give me one of these topes, then there's a sublattice of this lattice that I drew over there, which I call L of P. So this is the Las Vegas face lattice of the tope. The small one, so that I think there are the 2 face lattices of topes. But there's enough, yeah, there are big face lattices and small face lattices. So this is the small one. So there's a definition in terms of covectors and whatever. But in this case, what you do is you just take everything in here that can be reached. That's a face of P. So it's the part of this picture that's a face of P. So this line B is a face of P. So this is in it, and so is C and D. But A is not a face of P, even though it does A touches the boundary of P, but is not a face of P. This point is a face of B, and so this is my L of P. Okay, so inside this lattice sits a smaller lattice, which depends on the choice of tope. And so inside the Bergman fan, there's a piece that corresponds to just taking flags. So this is contained with something. And this is defined to be the union of all flags. Now, instead of taking flags of the matroid, I take flags that are inside the sublattice. So in P, and I take the corresponding cones and also all the subcones and so on. So this was studied by in some version of the language studied by the is this the reason why you considered the first time? Right, yes, yeah. So the nicest answer requires this choice, but you can also depends. So the answer depends which basis you pick. So the particular basis that I want to talk about will require these choices. There is another basis you can calculate with, and you wouldn't need the real structure. Yeah. So a little proposition is what happens if you give me two topes and you ask how these pieces inside the how they intersect. This is somewhat a technical thing. So this, it turns out that the intersection of two things of this type for two different topes, you give me two topes and you intersect two of these things inside the Bergman fan. It turns out that it's canonically a union of pieces each labeled by a partial flag. Flag in LP or LQ. And what is this thing? Is union of all the cones, all the maximal cones where the flag refines the partial flag. I suspect this is maybe familiar to, though I have not found this before.
What is GPQ?
So there exists a set, right? So I'm asserting that there exists a set GPQ, such that this is true, and also that these pieces are basically have no maximal cones in common. So sigma G intersects G prime dot lower dimensional. Minus one. So they don't, so you can canonically decompose this polyhedral set, this fan. You can canonically decompose this fan into these subfans so that they only intersect along lower dimensional faces.
The name of sigma p is the positive part of sigma. What was the name of this object?
I think it's called positive Bergman fan. If usually you pick M to be an acyclic oriented matroid and P to be the positive tope in this oriented matroid, then you would call this thing the positive Bergman fan of the oriented matroid. Yeah, so I'm going to describe two operations that goes from fans inside this space to basically to rational functions. One's called the Laplace transform, and that takes a cone to the following expression. Which is a function in y. So it's so the Laplace transform is some integral function. So once you give me a pointed cone, I can take y to be something in the interior of the dual cone so that this thing is always positive. Then this integral will converge, and it will converge to a rational function. So it will equal to a rational function. But for the particular case of the cones that we're looking at, these cones, it turns out that it's actually pretty easy. You can just take this as the definition. It's just the product over 1 over a bunch of these A. So the A's are my Y's. I should put A here. So my parameters A are they're labeled by the elements of the ground set E, and those are the denominators. So that you just look at the generators of your simplicial cone, and if it's unimodular, this is the formula for the integral. So that's one operation. Other operation is discrete Laplace transform. And this operation is you take all lattice points inside the cone with V to the E, and you take the monomial in B's that corresponds to those lattice points. So if this has some integer coordinates, you take B1 to something, B2 to something, and so on. And there's also a formula. There's also a formula for this. There's some sign, same sign of. Right. Oh, actually, after you put in the sign, I think I wanted to have no sign. 1 to the r minus 1. So if you try to take the and here BF is the product of all things in the flat of these. Yeah. And both of these are really easy. There's nothing hard about either of these. Great. The theorem is that the first part is for a particular basis, which I haven't told you about yet. But this basis is of the so they are elements inside this cohomology of an Euler-Solomon algebra. With respect to this basis, the pairing is given by this Laplace transform. Let me put it's basically this L of but there's some signs here. And another theorem says that this is, if you know what it is, it's something called Schechtman Varchenko contravariant form.
The sum of all cones in that time?
Yes, so you can so this is one of the cool things about it is that this Laplace transform here, it's just this integral over the whole thing. So it doesn't really matter what the fan structure is on it. Yeah? So it actually only depends on the support actually. So in fact I can write the support here. But what you can do is you can take the cones that appear in this description and sum over all the cones that appear. And the second part of the theorem is that if you do the same thing in Betti, you take the Betti homology intersection pairing, then it's the same thing, but you have to do this discrete Laplace transform, except that it's slightly harder. So it's this, what the symbol I used, is this Laplace transform, discrete Laplace transform. But I'm going to put this monomial factor and a sign that appears in front of it. So this is just some to a partial flag G. It's just some monomial in B, some particular monomial in B. So instead of the way to think about it is you're counting lattice points in the support of this thing, but you have to shift it slightly. And this shifting slightly has to do with having to choose a branch of the function. So if you chose a different branch, you would do a different shift. But there is a particular choice of shift that makes this into symmetric bilinear form. So one question I have for the experts, especially experts in tropical geometry, is whether some quantities like this for tropicalizations of other varieties might have been studied before. Is this something that's a thing that can be done outside the setting? And I don't know whether something like this can be formulated for other tropicalizations. Maybe tropicalizations that satisfy some niceness properties. But the reason to formulate it in this way, there's actually many different ways to write the answer. The reason to formulate it in this way is exactly because I was hoping that maybe this does admit some generalizations. Okay.
Like a piece are spanning sets or a basis?
Yes. So let me explain that now. So these two let me. So this H top view. So the dimension of this is this beta invariant. One way to find so there's one way to find a set that has the cardinality of this, which is something called beta NBC basis. It turns out the answer is a little bit nicer in a different basis for both of these, which are a basis that's the number of banded chambers. So I'll let this to be for an oriented matroids will be the banded pulse with respect to the infinity. So this is an affine matroid, affine oriented matroid. I take the banded topes. Then the cardinality of this is the beta invariant. And for both examples, my preference is to compute this as a matrix on a basis that's naturally indexed by this. Now down here, this one is really just indexed by topes. So these topes themselves are locally finite cycles. Over here, this is an upcoming work of myself and Chris which let me formulate here. For each top of an oriented matroid, there's a macro, the canonical form in the sense of positive geometry, canonical form omega p inside here. If you take so I don't want to say too much about positive geometry, but to be a canonical form is basically it's a statement about where the residues are. So by specifying where it has poles and what the residues at those poles are is uniquely determined. And the feature of it is if you take, and there's sort of two parts to the theorem. The first part is if you take P, and I'll have to explain what this means. Omega P such that this is a basis of D M and omega P is a basis of the cohomology of the Solomon complex. Yes.
Yeah,
Yeah.
I think I got a little bit lost in notation.
Yeah.
Is this equivalent to or related to the CHY integral? If you have a.
CHY integral is this top one.
Yes,
Yeah. Yes.
Okay, great.
The two bases are related in some way by period map?
Not by a period map, but by there is a sort of nearly canonical isomorphism between So find a normal crossing compactification of U. In this case, the cohomology is mixed Tate. In fact, it's better than mixed Tate. It's kind of pure, like it's mixed Tate concentrated in a particular weight. And under those conditions, there's an isomorphism between the cohomology and the relative homology. The relative homology of the whole thing relative to the boundary. So under some conditions, and it's basically because there are spectral sequences for both you can compute this with a spectral sequence and this with a spectral sequence that depends on the combinatorics of the stratification at infinity, and they're kind of the same. They're kind of the same spectral sequence, and under this sort of Tate hypothesis, you can just combinatorially match them up. And what happens is that this omega p gets mapped to this p, which is a relative cycle in here. So there's no twisting in this statement. So that's how they match up. So this is the cardinality of this set is the beta invariant. The cardinality of this set is the Mobius invariant of the matroid. And one thing that's has the same cardinality as the Mobius invariant is this are the topes that avoid a generic extension. So actually I can draw it over here. So you take a generic extension of the matroid, which is you just draw some hyperplane. You draw some hyperplane somewhere else, and you find all the topes that do not intersect it. This was a bad choice because if it's generic, they have to intersect somewhere down here. Yeah.
So this, you're about your theorem there?
Yes.
Does it then have the form, the canonical form?
Yes.
Does it has singularities on not just it's a polytope, right? You have a polytope, and so.
Yes. Yeah. So the canonical form of P will have 3 simple poles and no pole at infinity.
And it doesn't have poles like for corresponding to wonderful magnification then, or no? I mean.
This is something you should ask Lizzie about. There's a paper recently about what happens if you take the canonical form of this and pull it back to the wonderful compactification and where are the poles.
Okay, and it would correspond to the usual M0 and CHY story in that case?
Yes, I mean, these are rational forms,
Yeah.
and this is a birational map, so the kind of the form up there is nearly the same as the form up down there. So what is something with the same cardinality as the Mobius invariant, whose cardinality is the Mobius invariant, is topes that don't get cut by this guy, which would be this one. This actually, it does cut this one, I just didn't draw it very well. So in this case, I did it right, hopefully, it should be that therefore, this set would be cut size 4 and this set would be size 1. Number of bounded chambers is 1 and the number of chambers that avoid a generic extension is 4. Okay.
Where's this T star? What is that?
Yeah, so these are topes that are bounded with respect to the infinity of the affine matroid. These are topes that are bounded with respect to an additional generic extension.
Is that the constant coefficient of the polynomial, of the characteristic polynomial?
Yeah, that's the concept.
Which homological degree omega p lives in?
You can, so there are 2 versions of this theorem. You can make it, you can make it either a basis of the Euler-Solomon algebra, or you can make it a basis of the reduced Euler-Solomon algebra. And the 2 bases are related by the Euler vector field. So there's some thing that goes from, if this is the usual Euler-Solomon algebra, and then you take so they're in the top cohomological degree. So you can take the I is equal to D plus 1, and then there's map like this to and there's an isomorphism minus 1. And so I'm trying to be open to not be so precise here about, but yeah, if you find a basis of this guy, you also find a basis of this guy, and the way they are related is by just contracting with the Euler vector field. Any other questions?
Just checking. So M is a complex manifold of dimension D.
A U is, but yeah.
U is.
Yes, yes, it's a complex manifold of dimension D. So it's the complement of a projective arrangement. The central arrangement that corresponds to a matroid is one dimension higher. But most of the talk is set in the projective arrangement. So let me. Let me state. Okay, so I want to state something else which I don't have a geometric explanation for. Is it turns out that with respect to these bases, if I take the inverse of them, I get really nice matrices that are when set up correctly turn out to sort of be even nicer than the original ones. So I will have to explain some notation for this. So instead of taking this, so I'm going to talk about, so there are two versions of this result, one for this one and one for this one. So I'm going to take this matrix, but instead of indexing it by topes that are banded, I'm going to I'm going to calculate it for topes that are banded with respect to a generic hyperplane. But I'm going to allow sum of AE to be not equal to 0. So I'll explain why this in a moment. So this thing, the inverse is given by, so by definition, the inverse is some matrix that I denote like this. And there's a simple formula for the inverse. Inverse is let me draw a picture. So everything, I mean, these statements are all for matroids, but all the pictures are for hyperplane arrangements. So if you give me the basis ABC, so ABC will be a basis of the corresponding matroid. If I pick this generic extension, then there's sort of one of the regions cut out by it is the banded region, so this region. This monomial will appear in the answer if both P and Q lie inside this banded region. So in this case, it could be P and Q are both this, P and Q are both this, or P is one of them and Q is the other one. Then that monomial will appear, and I sum over all bases where this is true. So that's formula 1. And then formula 2 is somehow I'm doing something even weirder. Again, is I'm going to temporarily do something. I'm going to allow the product of these monodromies to not equal to 1 for this result. But there's still a well-defined thing using this theorem. So using this theorem, using these theorems, this Laplace transform, these Laplace transform are defined without this. That's why I'm working in this ambient space R to the E. Then this thing, so plus the inverse is noted like this. And what's the formula for this thing? It's equal to the sum of two monomials, it's always a binomial, and it's a sum of two monomials in B's, which correspond to the hyperplanes that separate P from Q, and also the hyperplanes that don't separate P from Q. So you give me, so in this version, you don't, you don't need a generic extension. But there is an infinity, so you do have a zero. You give me two regions. This is P and this is Q. You ask what are all the hyperplanes that separate P from Q, and it's A and B. So P Q is equal to A. Oh, this is really horrible notation. B sub A, B sub B. And the other monomial is everything else. So there's a C, there's a D, and there's also zero. So it's B, C. So those are the entries of the matrix. And so these results only apply when you make the matrices bigger. There's a bunch of explanations for this. So this one, you make the matrix bigger by looking at all chambers, basically by looking at a basis for not the cohomology of the Euler-Solomon algebra, but for the Euler-Solomon algebra itself. You calculate this thing, and it has a nice inverse. And this thing, you're even more greedy. You actually you basically take all topes, all topes up to negation of the oriented matroid, and take the inverse of that matrix. These matrices are sort of, you have to relax this condition here about the monodromy. Otherwise, these matrices will be low rank. The rank of these matrices will be the beta invariant if you impose this condition. But if you don't impose it, then they turn out to be invertible matrices, and they're sort of local version. These things where you allow the monodromies to sort of not multiply together, they're sort of local. The local versions of these calculations for the central arrangement that's one dimension higher. So I think I have behind here.
I have a notation question.
Yeah.
There you have A to the power of B, and here I have a B subscript some set.
Yes. Yeah. They're the same notation. It's just that I previously defined an A sub F, which is additive. And just for the A's, I needed both notations. So A sub F is sum of all the residues corresponding to A.
Like B of the word.
Yeah, sorry, but yeah, that one is product. So that one is the same. That one is, so for B's, usually the notation is multiplicative, and for A's, the notation is usually additive. But in this special case, this A sub B, this thing is a product. Yeah, sorry. So here are two of the matrices that this is about the deRham one. So this is deRham cohomology. This is what I call deRham homology. And the kind of things that you see here are these are the way you should read these is that the factors correspond to these rays in the Bergman fan, and this term in the answer, so D, B plus D plus E, that's a little flag, and that's the flag. Let's draw the flag. So D is this flag here. So this flag on the boundary of one contributes this term to the intersection form. And then there are some other terms. So there's a bunch of different terms here. And so this 5 by 5 matrix is this matrix here, which is the and I'm imagining that what I did is I put the generic extension at infinity when I drew this picture. So the bounded arrangements are the things that just literally look bounded. And the inverse of this matrix is equal to this matrix over here. Which I couldn't fit the whole matrix in, so I only drew a little bit. What does one of these entries look like? So this is the entry for 1 and 2. So those are the bases that correspond to simplices that contain both 1 and 2. if I did it correctly. So there should be, like this should be one of them. So that's C, AC. So this triangle is ACD and it contains both 1 and 2. So it's one of the terms in here. Yes.
So this is the KLT, right? And the question is,
This is okay. So for the case of the complete graphic matroid, this matrix was studied in physics before, which is the reason why I knew that I should do this for an arbitrary matroid. This is the KLT matrix with one of the particles being taken off shell. That's the technical term.
so I guess the question is, under what assumptions can you relax, or what's the, that's this very special hyperplane arrangement. So like, could you remind me of the assumptions for this? What's the most general hyperplane arrangement in which this?
No, this applies to
Anything?
Yeah.
Like not,
Yes.
okay, anything
just
else?
even to not. I'm saying it's true even for something that's not a hyperplane. It's just true for matroids. For oriented. To state this particular theorem, I need an oriented matroid.
Okay, very cool.
So one problem that I have is so the reason why I sort of insist on saying that there's a Betti pairing and a deRham pairing is that I think that there's 4 pairings, not 2 of them. 2 of them have been studied before, and I think that there should be 2 more. But I don't know what the independent definition of these pairings are right now. So they're labeled. So it's a pairing on kind of a dual group. So this is happening in cohomology. I'm calculating cohomology. So what I'm doing here to calculate this is I'm changing one of the forms to a compactly supported form. I'm integrating over this complement hyperplane arrangement. I get these numbers pop out. So this is happening in the corresponding dual homology group. And I'm getting something that's in some sense even more positive, even nicer than the original problem. There are no signs at all in this, and that's true for both. This thing. When you set it up correctly, both of these things have no signs in them. I should also say that this one. If you kill this term, this is called Varchenko's bilinear form. So if you only take one of the 2 monomials, so if you let's just put it down. If you do P, Q, D, and then you specialize B0 to 0, then this is something that's been studied before. It's bilinear form on a matroid. And now that I found this, so you can either see it the other way around. I found some geometric interpretations of this bilinear form. I'm wondering, I found a geometric interpretation of the inverse of this bilinear form. I'm wondering what the geometric interpretation of the original one was, and it's kind of not clear to me right now. But it seems like it should be independently. There should be a geometric understanding of it because it's positive. It's it's very hard to take an inverse of a matrix with all kinds of signs, and it pops out with just plus signs. Yes.
So this is all pre-wonderful compactification, that matrix you have there. It's just the hyperplane arrangement. You're not compactifying.
Okay, so the definitions of both of these forms do not depend on the compactification, but these formally, it depends on the support of something inside the Bergman fan. How you triangulate or how you divide this into cones depends on your compactification. So we have a preferred choice of maximal wonderful compactification that will lead to some particular formula for the answer. In the case of the complete graphic matroid, the formula that you know actually comes from the minimal wonderful compactification, but the formula that I like actually comes from the maximal wonderful compactification, and so you get a different formula for phi cubed amplitudes doing that. I will show it in 2 weeks. I will show you that formula that you get for amplitudes. Yeah. But every choice of wonderful compactification will give you a formula for this. I'll stop here. Thank you. Yes.
So this identity in the end, basically the inverse of the matrix, can you phrase it in purely combinatorial terms?
Yes, because the proof actually is, it holds the matrix, so the proof is basically using something about the topology of the links of various bases of these complexes. Like basically you need to calculate to prove either one of these inverses, what you have to do is you have to understand what these intersections look like, and you basically need to know Euler characteristics of all the kinds of subcomplexes of this.
And what I don't mean the proof, I mean the statement in the end, because it looks it looks like a clean statement, basically. You have some identity things that depend on your arrangement or whatever.
Yeah, it's purely combinatorial. I mean, as I said, one of the this thing where you take a matrix. So this matrix, Varchenko's matrix, is you take a matrix indexed by chambers of an arrangement, affine arrangement, and you just write down a monomial corresponding to which hyperplanes are separating two chambers. It's an extremely simple thing. In his original paper, he tried to invert it, and he got some partial results. His partial result is that when you invert it, the only possible denominators are the ones that you see in this. So he knew somewhat part of this theorem. So he had like half of the paper was trying to invert this matrix. Yeah.
Why did you want to invert?
So what he really wanted to do, and he did do, was to calculate the determinant of this. And so there are determinant formulas for all of these. And so he has a closed expression for the determinant of this form with respect to the lattice that stand by exactly these chambers. And he also has a formula for the determinant of this form. For this one is a result of Schechtman and Varchenko. For this one is a result of Varchenko. So he wanted to invert it to know which factors could appear in the determinant.
Yeah, maybe one last question. Well, maybe two. The niceness depends on the choice of basis for the bounded chamber. Is that right? You chose the basis and then that's a very good point. There are many other bases that are that have cardinality equal to beta of M or Mobius of M or one of these other things. For this one, there's kind of for this one, if you ask for the inverse, yes, you have to choose one of these bases. That you can't just choose a random basis of it. But for the question, let's say for the determinant, it only depends on the lattice spanned by your basis, and there is a natural Z form of this guy. There isn't a natural Z form of this guy, so there is no natural determinant to take down here. Yeah, but these guys are defined over Z. Yeah, for a random basis, I don't know how to invert these matrices. And for example, if you do NBC basis and you invert them, you get signs. It's only with this. It's only with these this basis in my theorem with Chris that the signs all disappear. And they're always plus when you choose the bounded basis. That's
it's always you only get plus signs.
You said that this matrix appears in the physics literature, and
what they wanted to do was they were trying to the original KLT matrix, for the complete graphic matroid that corresponds to the moduli space of n-pointed rational curves. What they were trying to do was they were trying to express something called closed string amplitudes in terms of something called open string amplitudes. So these are related to the period matrices P sub A that I wrote down before, and the open string matrices is just one of the P sub A. The open string amplitude is one of the P sub A's. The closed string amplitude is related to not taking the dual. So instead of taking this, the dual is this. There's another thing that you can do is to take complex conjugate. So there's another thing. There's another very closely connected connection, which is you take complex conjugate of all the parameters. And there is also a different pairing between your original connection, the cohomology of your original connection and the cohomology of this connection. And the resulting things you get are called closed string amplitudes. what they were trying to write was a formula that that looks a bit like, so you want to write closed string amplitudes in terms of open string amplitudes, and the coefficients looked a lot like the coefficients that appeared in that beta function formula. They didn't write the answer like this, but this is the reason I did this inverse is I knew that it was an inverse that was important. Yeah.
There are no more questions.